Registers are nothing more than a storage unit used to temporarily hold information until information is needed. The most common storage register is the shift register. There are several different circuit configurations that are called shift registers. They are classified by the method which data inputs and outputs to and from register. For example, shift registers may be classified as serial in, serial out, serial in, parallel out, parallel in, parallel out, and parallel in, serial out. As you can see, the shift register can convert data from serial to parallel or from parallel to serial. To illustrate how the shift register can accomplish this, we will examine a typical circuit. Here we see a simple circuit consisting of a keyboard encoder circuit, two shift registers, and a decoder driver. Note that the first shift register, a parallel in serial out, receives data from the keyboard encoder in parallel, then transfers the information in serial to the next shift register. This register is a serial in parallel out device. The serial in parallel out shift register receives the serial data, then transfers the information in parallel to the decoder driver device. To better understand how these registers were able to convert from parallel to serial, then vice versa, we will examine the register circuit. Here we see a circuit which is capable of serial in and either parallel out or serial out capabilities. Notice that this circuit consists primarily of clocked D flip-flops. When used as a serial in, serial out shift register, the parallel output lines Q1, Q2, and Q3 are absent. As was just mentioned, the serial in, parallel out shift register consists of a cascade chain of type D flip-flops that have their clock lines connected. The parallel outputs are labeled Q1, Q2, Q3, and Q4. If you recall the rules for type D flip-flops, the data can only be transferred from the input to the Q output when the clock input is high. Even if the input changes, the output will remain the same as long as the clock input line is low. Basically, the Q output retains the last valid data that was present before the clock pulse went low. Now let's examine the operation of this circuit as a serial in, serial out shift register. We will begin with a high followed by 3 lows at the serial in input. At the occurrence of the first clock pulse, the input line is high. This high clock signal causes the data to be transferred to the Q output of the first flip-flop. When the second clock pulse arrives, the flip-flop 2 will see a high at its data input, and flip-flop 1 will see a low at its data input. This causes the output of flip-flop 1 to go low, and the output of flip-flop 2 to go high. The third clock pulse results in a low at the data inputs of flip-flop 1 and 2, and a high at the data input of flip-flop 3. This results in the output of flip-flops 1 and 2 going low, and the output of flip-flop 3 to go high. And when the fourth clock pulse arrives, flip-flops 1, 2, and 3 will output a low, and flip-flop 4 will output a high. Notice that in the serial in, serial out shift register, that the single high condition was propagated through the entire shift register one stage at a time. However, most computers will use a parallel form of data entry since it is considerably faster than serial transmission. This is due to the fact that the information must ripple through the entire shift register in the serial in, serial out device. Here we see a parallel in, parallel out shift register. Notice that a common clock signal is used and that the input and output of each flip-flop is separated from one another. When the clock signal swings high, the information placed at each of the data inputs is transferred to the Q output of the device. As you can see, the process of transferring information is much faster using the parallel in, parallel out register as compared to the serial type device. There are a wide variety of shift registers available on today's market. We will examine only a few in this video. Here we see the SN7491A, which is a serial in, serial out 8-bit shift register utilizing transistor logic circuits. This IC contains 8 RS master-slave flip-flops with input gating and a common clock driver. This register is capable of storing and transferring data at clock rates up to 22 megahertz while maintaining a typical noise immunity level of 1 volt. Power dissipation of this device is around 175 milliwatts with a fan-out of 10 from the outputs. The clock pulse inverter causes the circuit to shift information toward the output on the positive edge of an input clock pulse. This enables the shift register to be fully compatible with other edge-triggered synchronous functions. Also note that there are two inputs on this device labeled A and B. One is used for the serial data in, while the other is used as the input control. Here we see the SN7495, which is a 4-bit right shift, left shift register, which is capable of serial in, parallel out, or parallel in, parallel out modes of operation. The SN7495 is a transistor logic monolithic 4-bit shift register which uses 4 RS master-slave flip-flops with internal clock buffers and control gating for either right shift or left shift operation. When the mode control input is made low, it allows the serial in input to become active, and it also enables clock 1 for a right shift operation. Also, when the mode control input is made low and no data is being placed at the serial input, then the register will load the data at its parallel inputs labeled input A through input D. When the mode control input is made high, it enables clock 2 for the left shift mode of operation. Data transfer occurs on the negative transition of the clock pulse due to the inverters being placed at the clock inputs of the RS flip-flops. Here we see the SN74166, which is an 8-bit shift register capable of parallel in, serial out modes of operation. The shift load input is used to determine if the device is loading serial data or parallel data. When the shift load is high, the device works as a serial in, serial out register. And when the shift load is low, the device is being operated as a parallel in, serial out register. During the parallel loading operation, clocking is accomplished on the rising edge of the clock pulse through a 2-input NOR gate. The 2 inputs on the NOR gate are labeled clock and clock inhibit. To prevent false clocking, the clock inhibit input should be high only when the clock input is high. The SN74166 has a shift frequency of 35 megahertz with a power dissipation of 360 milliwatts. We will now pause for a short review to reinforce the important concepts of the registers just discussed. All registers are basically a storage unit used to temporarily hold information until the information is requested by another part of the digital system. The most common storage register is the shift register. Shift registers are generally classified by the method in which the data inputs and outputs to and from the unit. The most common shift registers found are the serial in, parallel out, parallel in, parallel out, and parallel in, serial out. Shift registers may be used to convert serial data into parallel data, or to convert parallel data into serial data. The basic register is nothing more than a series of flip-flops configured to store multiple bits for future use. Shift registers are available in a wide assortment of sizes. Even though shift registers with 1024 bits are common, their basic operation will remain the same. This concludes review number 3. Next, we will examine some of the common displays found in digital circuits. All registers are basically a storage unit used to temporarily hold information until the information is requested by another part of the digital system. The most common storage register is the shift register. Shift registers are generally classified by the method in which the data inputs and outputs to and from the unit. The most common shift registers found are the serial in, parallel out, parallel in, parallel out, and parallel in, serial out. Shift registers may be used to convert serial data into parallel data, or to convert parallel data into serial data. The basic register is nothing more than a series of flip-flops configured to store multiple bits for future use. Shift registers are available in a wide assortment of sizes. Even though shift registers with 1024 bits are common, their basic operation will remain the same. This concludes review number 3. Next, we will examine some of the common displays found in digital circuits.